Manish, you can see my slides, right?
Yes, sir. Yes, sir.
Good morning, everybody. Welcome to the very first session of our International E-Conference on Advancement of Physical Science. It is an honor to be graced by the presence of Dr. Ajith Parameswaran, who is here to speak about the recent results from gravitational wave astronomy. I would like to welcome one of our conference coordinators and assistant professor of Parameswaran College, Dr. Manish Michael sir, to chair this session. Sir.
So good morning to one of all. So respected the speaker of the section, Dr. Ajith Parameswaran, dear faculties from various colleges, research colleges, and dear participants. So first of all, I would like to welcome you all to the first technical section of this international conference on recent advances in physical science. So to start the proceedings, we have a very eminent resource person, Dr. Ajith Parameswaran from International Center for Theoretical Science, Bengaluru. So it's my great pleasure to introduce Dr. Ajith Parameswaran before you. So as we all know, he has the expertise in gravitational wave astronomy. So the gravitational wave astronomy is nowadays treated as the new opening, or it is a new window to the universe. So it's my great pleasure to introduce the speaker. Dr. Ajith Parameswaran took his PhD from Max Planck Institute for Gravitational Physics in Germany. And after that, he has the postdoctoral research experience from the California Institute of Technology, USA, and the Max Planck Institute of Gravitational Physics. His research interest belongs to the different aspects of gravitational wave astronomy, the modeling of gravitational wave sources by combining the analytical and the numerical relativity. So the interpretation of gravitational wave observation, the test of general relativity using gravitational wave observation and astrophysics are some of his research interests. And he is also a member of LIGO Scientific Collaboration since 2004. He had directly contributed to the detection of the gravitational wave by the LIGO Observatory. He has more than 50 articles in peer-reviewed journals, over 3,000 citations. And it is very important to mention that he was one of the co-author of the paper, which is published in Physical Review Letters in 2016. That paper first reported the detection of gravitational wave. And some of his professional recognition includes the N.R. Sen Young Award by the Indian Association for General Relativity and Gravitation, the CIFAR Global Scholarship by the Canadian Institute for Advanced Research in 2017-2019, Special Breakthrough Prize in Fundamental Physics in 2016 as part of LIGO collaboration. So with immense pleasure, on behalf of the Department of Physics, Parameswaran College and Stride MG University, I invite Dr. Ajith Parameswaran to deliver his lecture in the topic, the recent research in gravitational wave astronomy. So welcome, sir. So this is over to you, sir. Okay, thank you.
Thank you very much, Manish, for the very kind introduction. Good morning, everyone. It's a great pleasure talking to you today. I thank the organizers for the kind invitation to speak at this conference. So I will try to give you a sense of the recent results that is coming out of the sort of newest branch of astronomy using the observation of gravitational waves. But I understand that the scope of this audience is quite wide. The scope of this conference is also quite wide, covering the entire physical sciences. So I'll try to give you a very long introduction. And then the last sort of half of this talk, I will try to sort of summarize some of the main aspects or the main result that came out of these gravitational observations in the last 5 years. So I apologize in advance for the experts in this audience. This is going to be a bit too trivial for them. So let me start with an introduction. The existence of gravitational waves was predicted as part of the general theory of relativity, which is the most accurate theory of gravity that we have right now. It's a theory of relativity as well as a theory of gravity. And as you know, it was proposed by Albert Einstein in 1950. We sort of celebrated its centenary year in 2015. In fact, the same year as the gravitational waves are observed. So this theory is still, something that is very difficult for most people to come in terms with. This describes gravity as the curvature of space and time. So it's a very dramatic departure from the more familiar theory of gravity that we all study in school, which is due to Newton, which describes gravity as a force between massive objects. And according to Einstein's theory, gravity is not described as a force, but it actually changes the properties of the underlying space-time in which events happen. And any massive objects, like an apple or other forms of energy, would introduce a curvature in space as well as time. And this is something very difficult to imagine because the space has 3 dimensions and the time has another extra dimension, and the space-time is a single object that has 4 dimensions. And it is very hard to imagine a curved 3-dimensional space or 4-dimensional space-time. But one can actually do experiments, one can do measurements to actually measure whether the space-time that we are living has a curvature or not. So a simple test would be, this is like a Gedanken experiment, it's like a thought experiment, where one could actually draw a triangle and see if the angles inside the triangle adds up to 180 degrees. This is what we study in school, like a Euclidean geometry, right? The angles inside the triangle add up to 180 degrees. And this is true only for a flat space. For example, if you were to repeat the same exercise on the surface of a football, you would see that the angles are actually larger than 180 degrees. So one could do some experiments to actually make a measurement of the curvature of the local space-time. And very, very far away from any massive objects, the space-time is completely flat. So all the axioms of the Euclidean geometry that we study in school hold true. However, in the vicinity of massive objects, the space-time is curved. And if you do the same experiment there, you would see that the space-time has a curvature. And this has a number of interesting consequences. So for example, the first observational puzzle that Einstein was able to explain using this new theory of gravity is the peculiar orbit of the Mercury, the planet Mercury. So we know that the Earth has a pretty elliptical orbit, that is a closed ellipse. And in Newtonian gravity, basically all the planets move around the sun in ellipses, that is the Kepler's laws. But in the case of Mercury, the ellipses don't close, they precess, they are not closed ellipses. And this is mostly because of the perturbation of the other planets affecting on Mercury. But even if you take into account the effects of gravitational effect of all other planets, one cannot fully explain the precession of the orbit of the Mercury using Newtonian gravity. And according to Einstein's theory, one could calculate these orbits, and it exactly explains the observed orbit of Mercury. So there was one very important observational puzzle that Einstein was able to naturally explain using this theory without doing any extra hit. Perhaps people can mute their microphones. Okay. And apart from explaining the existing, unexplained observations, Einstein's theory was able to predict a number of new phenomena that were not found to be existent until then. And one is that gravity bends light. So we know that light usually travels through straight lines. That's because the shortest points between any 2 points in a flat space is a straight line. However, if the space is curved, or the space-time is curved, the geodesics, so that space-time, the shortest distance, the curves that connecting 2 points through a shortest distance are not straight lines. So they are called geodesics in general. And light basically travels through geodesics of this curved space-time. And one could actually have physical situations where this curvature would introduce a bending of the path of the light. So for example, if there is a distant star whose rays are basically going through the vicinity of the star, of the sun, because of the curvature of space-time produced by the mass of the sun, the light gets deflected. And an observer who is looking at this distant star from this other side would see that the apparent position of the star has shifted. So if you, for example, are able to see stars in the vicinity of the suns, you would see its apparent position shifted. And one has to wait for an eclipse, a total solar eclipse, for this to observe, because you cannot observe starlight in the vicinity of suns. And this is what was done in 1919 by a team, like 2 teams of astronomers, British astronomers led by Arthur Eddington. And they basically observed the position of stars in a cluster, of a stellar cluster, in the vicinity of the sun during the eclipse. And they compare it against the relative position of the same star cluster, this cluster of stars, when this cluster appeared in the night sky. So this is an actual photograph taken by these astronomers, Eddington and colleagues. And you could actually see the stars in this photograph if you squint. But there is I made a simplified version of this photograph, a cartoon version of this, which shows, for example, a juxtaposition of these 2 photographs of this cluster of stars, one taken during the eclipse and another taken when the same cluster of stars appear in the night sky. So that is shown by these blue stars here, when this called a reference photograph. And during the eclipse, their position is shown by these red stars. And you can see that during the eclipse, the relative position of the stars have been shifted. And the closer the stars are to the limb of the sun, the larger is the angular shift. So, and this shift can be predicted using Einstein's theory, because it depends primarily on the mass of this lensing object, or the sun, basically. And since we know the mass of the sun, we can actually calculate the deflection angle. And these observed angles were consistent with the prediction of Einstein's theory. So that was one of the many new observational predictions that Einstein's theory put forward. And there are a number of such observational predictions were put forward by the general theory of relativity during the subsequent decades. This includes things like the gravitational lensing of light. This is the second photograph, so it's a remarkable example of that. Gravitational time dilation, or gravitational redshift, which again was not only verified by very, very accurate laboratory tests, but it has become part of our modern technology. For example, for the GPS to work, one has to include the effect of gravitational time dilation. And another is the existence of black holes in the universe. And now we know that our universe is basically littered with black holes. And this one movie shows a series of astronomical photographs taken over 2 decades, which were combined to make a movie. And this shows the movement of stars in the galactic center. And these stars appear to be moving around a dark object. And from the motion of the stars, one could infer the mass of the central object. And it turns out to be about 4 million solar masses. So our best inference is that our galactic center contains a supermassive black hole of about 4 million solar masses. So there are several such observational evidence that black holes exist in the universe. And in fact, this remarkable observation was awarded the Nobel Prize last year for physics for the discovery of this supermassive black hole at the center of our galaxy. So similarly, I just want to give you a sense that Einstein's theory has predicted a number of very interesting and exotic phenomena, including black holes, expansion of the universe, gravitational time dilation, gravitational lensing, etc. And all of these observational predictions have been verified with really remarkable accuracy over the last century using a number of astronomical measurements as well as some laboratory tests. The last observational prediction that was verified by a direct observation is the existence of gravitational waves. So gravitational waves are one of the many solutions of Einstein's field equations, which are the equations predicted by Einstein's theory of gravity. And these are basically wave-like solutions to Einstein's equations in mathematicians' language. But in terms of a physical picture, they are basically freely propagating oscillations in space-time geometry. So you can think of them as ripples propagating on space-time, but the ripples are on the geometry of space-time itself. So curvature in the space-time is propagating with the speed of light. And any motions of massive object with some acceleration would cause the generation of gravitational waves. So if I'm moving my hand, I'm creating gravitational waves, but these are too weak to be detectable. So the likely detectable sources of gravitational waves involve massive and compact objects like black holes and neutron stars, moving with very large velocities. For example, a binary system of two black holes or two neutron stars. But there are, depending on the mass scale of these objects, gravitational wave sources exist in a variety of frequency bands. So there's a whole spectrum of gravitational waves, just like there is a spectrum of electromagnetic waves going from all the way from radio to gamma rays. So here is a diagram that shows the spectrum of gravitational waves and possible sources of gravitational waves and their detection methods. And just like we need different kinds of antenna to detect electromagnetic waves of different frequencies, you need to have different kinds of antenna to detect gravitational waves of different frequencies also. So for example, the technique for detecting radio waves is very different from the technique for detecting gamma rays, right? So here is the spectrum of gravitational waves going from the lowest frequency to highest frequency here. And we have so far detected gravitational waves in the high frequency end also, which is a frequency of a few hertz to a few kilohertz. And here, the most likely sources of gravitational waves include in spiraling systems of compact objects like black holes and neutron stars. But there are also other possible sources like spinning neutron stars, rapidly rotating neutron stars, or collapse of massive stars in our own galaxy, producing a supernova, and so on. But if you go to even lower frequencies, there are other possible sources like binary systems of supermassive black holes, the kind of black holes that exist in our galactic center. And we do have evidence that such supermassive black holes can come in pairs and in binary orbits. And if they move around each other, then they produce gravitational waves, but with much lower frequencies. And we do not have any detector for detecting such gravitational waves yet. But there is a planned space-based gravitational wave observatory called the LISA, which would fly in the next 10 years, which will detect gravitational waves from these supermassive black holes. There are also even more massive supermassive black holes that have about 1 billion solar mass. And again, we have seen evidence of such black holes in our own neighboring galaxies. And such binary systems of such supermassive black holes would create gravitational waves of even lower frequency. And there are a large number of radio telescopes forming what is called a pulsar timing array, which look for signatures of gravitational waves on the arrival time of pulses from several millisecond pulsars. And so they have been operating for the last decade or so, and people hope that they might make the first detection of gravitational waves in the next few years. In the extreme low frequency regime, or wavelengths comparable to the size of the observable universe, again, there could be gravitational waves, and these could be produced by the Big Bang itself, or the processes happening soon after the Big Bang. And these could actually have an imprint on the polarization of what is called the cosmic microwave background radiation. People have observed the really made remarkable observations of the cosmic microwave background radiation, as well as its polarization, but we have not seen its the imprint of gravitational waves on the polarization of cosmic microwave background radiation yet. But again, that's another frontier that is happening these days. So to summarize, there is a whole spectrum of gravitational waves, and there are different kinds of techniques used to detect gravitational waves that are all ongoing. But so far, the first success came from the observation of the high frequency regime, and that is using laser interferometer detectors, which I'll come in the next few slides. So here, these detectors basically work based on the understanding that gravitational waves are basically propagating tidal forces. So just like the moon introduces tides on the Earth, which basically deforms the Earth into an ellipse or ellipsoid, gravitational waves passing through the Earth would deform the space-time in a characteristic way. So for example, if you have a ring of particles that are free to move, freely floating particles or freely falling particles, then this ring would get deformed into an ellipse shape. So it gets stretched in one direction and compressed in the orthogonal direction. This is called a quadrupolar deformation. So here is an animation that shows how a ring of freely falling particles will be deformed when a gravitational waves pass through the space-time. So basically, you are using these particles as tracers of the deformation of space-time. Just like, for example, you can put a ball, a rubber ball, or a plastic ball on water, and when there are water waves, this plastic ball would go up and down. So this plastic ball is a tracer of the height of the wave. So you can think of these test particles as a tracer of the deformation of space-time, or the height of the wave, the height of the gravitational wave, and the height in this abstract coordinates. And such deformations can be measured using what is called laser interferometers. And this is something that most of you must have seen or studied in college. Interferometry is a very standard technique in making precise length measurements. So we have a laser beam that is the best source of monochromatic light, and that basically shines laser on a beam splitter, which is basically a half silvered glass that would split half of the light into a reflected beam and a transmitted beam. And here you put two mirrors, close to perfect mirrors, that would reflect these light backwards. And because the light also has a wave nature, it produces an interference pattern. And initially, the length of these two arms can be adjusted such that the interference is destructive. So basically, no light gets leaked into this, what is called a dark port. And when a gravitational wave passes perpendicular to the screen, basically it deforms a space. So basically it stretches space in one direction and compresses the space in another direction. And this will basically cause a relative change in the path length of the light, right? Because the light would take a longer time to go and come back in this direction as compared to this direction, which will basically make a change in the interference pattern. And it will cause some light to come through this dark port, which is originally a dark port. And you can read this light using a photodiode, and you can basically record a time series of this brightness, which would basically measure a time series of these oscillations of these mirrors, which is your gravitational wave signal, basically. So delta L by L is the strain induced by the passage of gravitational waves. So it's a standard technique, but the challenge is that the expected change due to the passage of a gravitational wave is extremely tiny. For example, the fractional change delta L by L, well, delta L is a change in the arm length and L is the baseline length due to the passage of a loud gravitational wave, in astrophysically loud gravitational waves, is of the order of 10 to the minus 21. The strain is like 10 to the minus 21. So this means that even if you have an interferometer as a kilometer scale, like L is 1 kilometer, the change induced by the passage of this gravitational wave, it's called delta L, is of the order of 10 to the minus 18 meter. So it's something 1,000 times smaller than an atomic nucleus. So if you want to detect gravitational waves, you have to have an instrument that should be able to measure changes in its length that is of the order of 1,000 times smaller than an atomic nucleus. So it's a very, very difficult measurement to perform. But scientists have built these extremely precise measurement devices called very large Michelson interferometers, and commissioned them, and they are operating with sensitivities better than what I talked about. So these are the aerial photographs of the LIGO observatories in the USA. There are 2 of them at the 2 corners of the USA, separated by about 3,000 kilometers. And these are basically L-shaped interferometers, Michelson interferometer, that has an arm length of about 4 kilometers each. Not about, exactly 4 kilometers each. And as soon as these interferometers started operating in a configuration called advanced LIGO with an advanced sensitivity, they made the first detection of gravitational waves. This happened in 2015. And this shows this animation shows the actual gravitational wave signal observed by the 2 LIGO observatories. So the x-axis is the time in units of seconds, and the vertical axis is, there are 2 of them, but if you look at this oscillating signal, it is basically the amplitude of the gravitational wave signal. And you can see that it has a very characteristic shape. So if you follow the frequency of the signal, it has a increasing frequency and increasing amplitude. And this is called a chirping signal. And in the background, you also see a time frequency decomposition of the signal. It's called a spectrogram. And then the vertical axis is the frequency. So you can see that this frequency is increasing as a function of time, as well as its brightness or amplitude is also increasing. So this kind of signal is called a chirping signal because it's similar to the chirping of birds. The frequency content is similar to the chirping of birds. This kind of signals. And this is a signal that is produced by the in spiral of 2 compact objects. So you have 2 objects, like for example, 2 black holes orbiting around each other, producing gravitational waves. And since they lose energy into gravitational waves, they come closer and closer because they lose their orbital energy into gravitational waves. And once they come closer and closer, because of the conservation of angular momentum, they have to rotate faster and faster. It's like Kepler's 3rd law. And when they rotate faster and faster, they generate more and more gravitational waves, which would cause them to spiral in faster and faster. So it's like a runaway process. And finally, these objects merge to form a single compact object, most likely a black hole, which is rapidly spinning. So this newly formed black hole would have some oscillations. And there are some like quasi-normal modes of these oscillations, would also have a shape which is of single frequency and exponentially damped amplitude. So we see all these features in the gravitational wave signal, even if you look at it by eye, but one could do much more precise by, for example, comparing this data systematically with theoretical models of the expected gravitational wave signals as produced by merging or spiraling in compact objects like black holes. And one basically computes these theoretical models by solving the equations of Einstein's theory. And by systematically comparing the data with millions of theoretical templates corresponding to different source parameters, like the masses of the black holes, etc., one can actually extract a lot of understanding of the properties of the system, the astrophysical process that produces gravitational waves. And by studying this signal, scientists have concluded that the signal was produced by the spiraling and the merger of two massive black holes, each weighing about 30 times the mass of the sun, in a very distant galaxy about 1 billion light years ago. So, and since then, so this was this discovery was made in 2015, and it's of course was a groundbreaking discovery. And the founders of LIGO, Ray Wise, who originally developed the idea of using laser interferometers for detecting gravitational waves. Kip Thorne, who pioneered a lot of theoretical work in the science of gravitational waves, and Barry Barish, who led the LIGO scientific collaboration as well as the LIGO project and brought into success in the early years, were awarded the Nobel Prize in 2017 for decisive contribution to the LIGO detector and the observation of gravitational waves. Since then, since the first observation in 2015, the LIGO and its sister observatory called Virgo in Europe have been collecting data for several observing runs and have detected dozens of gravitational waves. Right now, LIGO and Virgo have detected of the order of 90 gravitational wave signals from coalescing compact objects, mostly involving black holes, but some involving neutron stars also. So here is a cartoon version of the compact objects discovered by LIGO and Virgo through gravitational wave observations. So vertical axis of this is the mass of these compact objects in solar masses. And all these blue black holes are the black holes discovered by LIGO and Virgo. And if you compare it against the black holes discovered by other astronomical observations, for example, using X-ray astronomy, these are shown by these crimson dots. And these are all observed by X-ray satellites from our own galaxy, while the LIGO black holes are always extragalactic. They are at cosmological distances. And you can see that these LIGO black holes are on average much more massive than these black holes discovered by X-ray observations, or LIGO have discovered a new population of black holes that astronomers did not know to exist until then. Similarly, the LIGO and Virgo have observed several binary neutron stars, as well as black hole neutron stars as well. And they all have produced some very, very interesting new science. So it's very hard to summarize all the science that came out of the LIGO Virgo observations in one talk. But let me just give you a few highlights. So these gravitational wave observations provided the first observations of merging binary black hole systems. So you have two black holes orbiting around each other, emitting gravitational waves and colliding finally, forming a new, more massive black hole. It's the first time we are seeing such systems in using any branches, any telescopes. We have no way of directly observing binary black hole systems that are merging using electromagnetic telescopes yet. LIGO and Virgo have observed also binary systems of mixed binaries, where there is one black hole and one neutron stars. Again, it's the first time we are observing such systems in astronomy. They have uncovered a new population of stellar mass black holes that are much more heavier than about 30 solar masses. As I told earlier, these crimson dots in this previous plots, which are the black hole candidates discovered by X-ray observations, they all have masses less than about 20 solar masses. It was a surprise for most astronomers that there are these like massive black holes that are like 50 solar mass or 100 solar mass exist in the universe. And indeed, LIGO observations have uncovered the existence of these more massive black holes. And there is at least one potential evidence of the existence of what is called an intermediate mass black holes. These are black holes that have mass more than 100 solar masses, but less than about 10,000 solar masses. Astronomers have speculated the possibility of these intermediate mass black holes, but there are no conclusive evidence of their existence yet. And there is this particular gravitational wave signal called GW190521. And by analyzing the data, scientists have concluded that this merger of these two black holes would have produced a remnant black hole that is going to be more massive than about 100 solar mass. So it's probably the first reasonably conclusive evidence of the existence of an intermediate mass black hole. There is another very interesting gravitational signal, which is called GW190814. These names are basically stand for the date of the observation. GW190814 means the signal was observed in 2019, August 14. So this signal, by comparing the data with theoretical models, scientists have concluded that at least one of the system has a mass of about 2.5 solar masses. So this is either the heaviest neutron star that we have ever seen, or the lightest black hole that we have ever seen, using any observation of astronomy. So we do not know whether this is a black hole or neutron star, but in either way, this is a world record in some sense. Apart from these sort of remarkable firsts, these observations have also allowed us to perform observational tests of Einstein's theory of gravity, the general relativity, in a regime that is inaccessible by all kinds of astronomical tests and any kind of astronomical tests or laboratory observations, because these compact objects producing these gravitational-based signals are extremely compact and extremely massive, and they are moving with speeds close to the speed of light. So you have these cosmic colliders of these extremely massive and compact objects colliding them at extreme velocity. So if we expect the general relativity to break down, this is one region. And so far, it appears that all the observations are consistent with the predictions of Einstein's theory. But our precision of doing these tests will only improve in the future. And it is not impossible that we will see some hints of the deviation of Einstein's theory. So whenever a new branch of astronomy comes into existence, it also brings in new mysteries or new questions. So the gravitational astronomy also has opened up new mysteries. One is that we know that these black holes, these heavy black holes now exist in the universe, but it is not clear how nature produces this extremely massive black hole, and in particular, binary systems of these black holes. And there are several possible astrophysical mechanisms for producing these binary systems of black holes. It is not entirely clear which of them is actually preferred by nature. And it's a very active area of research, and we don't have the answers yet. And so it's a very, very active area of research, and the literature is expanding on a daily basis. But if you want to have a nice and accessible summary of a lot of the science from the LIGO scientific collaborations papers, I would encourage you to read these science summaries. The URL is given below, which provides some very accessible science summaries of all the papers written by the LIGO and Virgo collaborations. So I should probably spend a little bit of time in discussing one observation, which is probably the most remarkable observation that LIGO and Virgo have produced, which is the gravitational wave signal from a binary neutron star system and its subsequent observation of its electromagnetic counterparts. So this signal was observed in 2017, August 17. And you can see the time frequency maps of the data, gravitational data, which shows this very clear and beautiful chirping signal, has an increasing frequency as a function of time. And this is a very exciting observation. But even more excitingly, the Fermi satellite, which is a satellite that looks for what is called a gamma ray burst, discovered a flash of gamma rays coming from the same patch of the sky about a second after this gravitational wave signal was observed. So this basically triggered a large number of telescopes to look at this patch of the sky, because astronomers were hoping for such an opportunity, because astrophysicists have speculated that some of the cosmic phenomena would produce both gravitational wave signals as well as their electromagnetic counterparts. And these two separate kinds of observations will contain very different and complementary information. And astronomers were waiting for such a signal, and it sort of came too early in some sense. So about 100 such telescopes observed this patch of the sky and detected its electromagnetic emission, or a flash of light in different frequencies, all the way from radio to gamma rays, in the next few weeks and months. And this was a remarkable observation because it sort of inaugurated in a large way what is called the multi-messenger astronomy. So here is a sort of a cartoon of what must have happened. This is like a time sort of running from left to right. You have two neutron stars. These are snapshots of what has happened during this merger. Two neutron stars orbiting around each other. And when they come producing gravitational waves, you can see this white signal. It's the gravitational signal observed by LIGO and Virgo observatories. And when they come and they lose energy into gravitational waves and come closer. And when they come very close, due to the tidal forces of the companion, each neutron stars get deformed, just like the Earth. So the moon creates tides on the Earth. And the tidal forces are so extreme that the neutron star basically gets disrupted. It gets ripped off. And this neutron star is comprised of basically nuclear matter, pure neutrons. And these neutrons are basically splashed away all around this newly merged object, which is likely to be a black hole. And this disk of nuclear matter basically gets accreted back, falls back to this newly formed compact object, probably a black hole. And this would launch a jet of high energy particles and photons, and which this satellite has observed as a gamma ray burst. And remaining this ejecta from this neutron star also expanded, and there are a large number of nuclear reactions happening there, which is called R process, rapid nuclear synthesis, where a lot of heavy elements are synthesized. So most of you must know that most elements in the universe are synthesized, most of the light elements in the universe are synthesized inside stars, including the carbon, nitrogen, etc., etc. But elements heavier than the iron cannot be synthesized in the interior of stars. And until very recently, people had speculated that these are produced in the collapse of massive stars producing supernovae. But now that we have more and more accurate estimates of the rates of supernovae and the physics of supernovae, it turns out that we cannot explain the observed abundance of heavy elements in the universe purely using core collapse supernovae. And recently, astrophysicists have proposed an alternative mechanism that perhaps a large fraction of the heavy elements in the universe are produced in the merger of neutron stars. And the electromagnetic observations following this compact binary merger, this neutron star merger, have concluded that, in fact, this merger has seen synthesis of heavy elements like platinum, gold, etc. And it has confirmed this hypothesis. In fact, there are estimates that were given that about an Earth mass size of gold was synthesized in the single merger alone. So it's a remarkable gold factory producing, very, very heavy elements. So such a single observation has provided a large number of very, very interesting signs. I have no time to go through all of this, but if you just Google for what is called the cosmic fireworks, then this is a graphic prepared by our colleagues at ICTS, and it has a lot of information on the signs of this neutron star merger. So that was my quick sort of short summary of the interesting science came from these LIGO Virgo observations of the last few years. But I also want to stress that the gravitational wave astronomy has only begun. These detectors like LIGO and Virgo have not yet achieved their design sensitivities. Their sensitivities are being improved. And as with each modest improvement in the sensitivity, we are greatly improving our observing volume, the area of the volume of the universe that is accessible to these observations. And in the next, if you just extrapolate our current progress, we would expect in India, which is the most exciting project for the Indian astronomers now, the gravitational astronomers at least now. And apart from these guaranteed sources of gravitational waves, we also expect the possible detection of new kinds of signals, like the detection of what is called a stochastic background of gravitational waves, or the continuous gravitational waves from spinning neutron stars, or the gravitational waves from a supernova if it happens in our own galaxy, etc. So it's a whole science that is waiting to be explored, and that the next few years will be very, very exciting. So I told you that depending on, there's a whole spectrum of gravitational waves, and one need different kinds of detectors to detect gravitational waves in all these different frequency bands. And so our scientists are already thinking about the next kind of detectors that would increase not only the sensitivity or horizon, but also the bandwidth of these our exploration of gravitational waves, trying to span the entire spectrum of gravitational waves. So there are the next generation gravitational wave observatories are being thought of, and some ideas involve going underground, building very large tunnels, like 40-kilometer long tunnels underground. This would improve our ability to get rid of the seismic motions of the Earth. And that's called, the idea is called the Einstein telescope. And there is a similar idea that is explored in the US called the Cosmic Explorer, which is to build something like a 40-kilometer LIGO, significantly increasing its arm length, going to really large scales. And when these detectors become operational, they would be seeing practically all the black hole mergers happening in the universe, because their sensitivity is so high that you can see the whole of the observational universe, at least in this frequency band. There is also an ongoing project, which is led by the European Space Agency, to build a space-based gravitational observatory called LISA. It's all funded and it's being progressed. And this will be launched in the next 10 years. And this LISA observatory will detect gravitational waves from supermassive black hole binaries, as well as what is called the extreme mass ratio in spiral, where you have a small black hole orbiting around a supermassive black hole, producing small perturbations in the space-time geometry of this large black hole. LISA would also detect other sources, like, for example, gravitational waves from white dwarf binaries from our own galaxy, and possibly some signals from the early universe also, more speculatively. So there are, and there are new kinds of techniques being explored apart from these more standard techniques also. So there's the whole field of experimental gravitational wave physics is also going very active. So let me stop here and summarize. So I try to tell you that the recent observations of gravitational waves by LIGO and Virgo have opened up a new branch of observational astronomy. So a huge amount of very interesting science have come out. I don't want to repeat these ones, but most interestingly, hundreds and possibly thousands of gravitational signals are expected in the next few years. And new detectors are coming to the picture, joining this global network of gravitational detectors, especially the LIGO India, which is a very challenging project for Indian astronomers. But it's also very exciting, because one has to have challenges to make interesting science also. So to building and operating this observatory involves the cutting edge in experimental physics and technology involving lasers, optics, mechanical isolation, quantum measurements, computing, etc. It also provides Indian astronomers and physicists to do some very interesting astrophysics and fundamental physics also. So there are opportunities for different kinds of scientists as well as engineers to contribute to this very exciting frontier observatory. And I encourage you to take a look at the website of the LIGO India for more information. At the same time, the global community is also expanding the horizon and the bandwidth of the gravitational observations by thinking and building observatories in different observatories in space and ground. So it's really a beginning of a new branch of astronomy and a new window to the universe, so to speak. So let me stop here, and thank you very much. I'll be happy to take any questions.
Okay, thank you, sir. Thank you very much for an informative lecture on gravitational, the basic concept of gravitational works and the detection methods and the lookup. So now the participant can ask questions. You can either ask directly or you can type it in chat box.
I can see one question already. So how can we pin the location of the source of gravitational waves in the sky? So that's a very interesting question. Unlike the case of optical telescopes, one cannot point the gravitational observatories to different parts of the sky. In fact, these observatories are broad antennas which are sensitive to gravitational waves coming from almost all directions in the sky. So if you want to detect localized gravitational waves, you need to have a network of detectors. And what you do is, we know that the gravitational waves travel with the speed of light. And we also know that the separation between the two detectors. For example, the two LIGO detectors are separated by about 3,000 kilometers. So the gravitational wave would take about 10 milliseconds to go from one observatory to another. So from the observation of the time delay between the observed signal from multiple observatories, one can triangulate the source in the sky. This is similar to how our ears work, right? So our ears basically measure the delay in the arrival of sound signals. And this is how our brain would process. And that's how we are able to locate the arrival direction of sound. That's why it's important to have two ears. So that is in a similar way, the more the number of gravitational detectors are there, the better is your accuracy with which localization can be done. That's why it's very important to have the LIGO India detector in the global array of gravitational detectors. So the next part of the same question is, what was the x-axis in the plot showing the new population of black holes and neutron stars? The x-axis has no meaning, just only the y-axis has a meaning.
Any further question?
Okay, see some.
So some other questions.
So one is in the spectrum, you said the wavelength of something like a binary supermassive black hole system is much larger than the wavelength of supernova. I'm confused with the energy expelled by supernova is much larger than the black hole, because I've heard that a black hole emits much larger than that. Right. So maybe you should repeat the question, but my understanding, so the question is whether the energy, so the energy radiated by a binary black hole system is indeed much larger than the energy radiated by a supernova. So I think the question is why it has a longer wavelength, not a shorter wavelength that you would naively expect. The reason is that is that the question? Christina, maybe you want to ask the question? Maybe I'll wait for Christina to bring up her mic, but meanwhile I can answer the other question. So Bhavana is asking whether the gravitational waves would also affect the time in the detectable range. Indeed, it does. So, for example, if you have a very precise clock, then one could actually measure the flow of gravitational wave because it would also have an effect on the time also. In fact, the interferometers, as well as in particular the pulsar timing arrays, are doing something like that. What they're doing is they're measuring the arrival times of several pulses from several millisecond pulsars. And when a gravitational wave passes through it, it basically causes a delay in the arrival time of pulses. So indeed, gravitational waves can affect the time. And in fact, the detection of gravitational waves using pulsar timing arrays are making use of this idea. Okay, Devika is asking the progress of ISRO in gravitational wave field and the current status of the future of LIGO India. I don't think currently the ISRO is invested in gravitational waves yet, but I know that there has been some proposals for a space-based gravitational waves observatory to ISRO by some scientists in India, but it's in a very preliminary stage. In terms of LIGO India has basically completed its acquisition of land, and sort of the building of the observatory is in progress, and it's currently waiting for the approval of this what I call detailed project report from the cabinet to start the construction of the observatory as such. The next question by Linu Mary is, why 4 kilometers or 40 kilometers selected for the length of the observatory? How is this length selected or calculated? So if you just look at the reasonable astrophysical rate predictions, then it is clear that you need to have something of the order of a kilometer. But if it's like 4 kilometers or 10 kilometers, basically restricted by your budget. So I think the first proposal for LIGO was envisaging about 10 kilometers, but at the end, one has to make compromises depending on the available budget and so on. So it's, off the order of a kilometer is arguable. You can actually argue based on some science, but whether it's 4 kilometers or 10 kilometers, it depends on various other constraints. And 40 to 40 is basically, you're targeting something like at about 10 times more sensitivity. So that is roughly the scale again. So Christina, do you want to ask your question about?
Okay, Christina, now you can ask.
So presumably your question is like, if the energy is high, why is not the wavelength shorter as you expect from, for example, quantum mechanics, etc. The reason is that the binary black holes certainly emit a larger amount of energy, and supermassive black holes emit more energy than stellar mass black holes, but over a longer period of time. So the whole time scales get stretched just proportional to the mass of the black hole. That's why the gravitational waves from a supermassive black hole system is longer, and the in-spiral happens over a longer time scale. I hope that roughly answers your question.
Okay, sir. Sir, may I ask a question?
Sure.
So actually, I have my doubt is regarding the field equation of Einstein field equation. So if in Einstein field equation, in the left-hand side of the equation, you have the Einstein tensor and the metric tensor. In right-hand side, you have energy stress tensor. So for black hole, I think the energy stress tensor, the value of energy stress tensor is equal to 0, right, sir?
Yeah.
So my question is there any condition when the energy tensor become negative in value? Is there any condition existing? Is there any possibility to become negative value for that particular tensor?
No, that would basically violate our, there's a particular positive energy condition. So for normal matter, you need to have the stress energy tensor has to be positive. So, but certain solutions of Einstein's equations require a negative stress energy tensor, but that we don't know what kind of matter would produce such negative stress energy tensor. So called typically exotic matter and so on. We don't know physically what such matter would be.
So this is actually one of the doubt asked by a 10th standard student who is studying in Parameswaran government school last day. So the same answer I was given. So there is mathematically you can say that there will be an existence. So it is the physical condition is very rare.
Yeah, a lot of people are fascinated by the science fiction aspect of it because of wormholes would require these negative stress energy tensor and so on.
So his question was, if there is the negative value for the energy tensor, so how the terms in the LHS of that equation is modified? That is the energy tensor, Einstein tensor and the metric tensor. How the term will be modified? That was actually his doubt regarding that question.
Yeah.
Okay. So if any other question? Okay.
Good morning, sir.
Okay,
Sir, first of all, thank you so much for a wonderful lecture, since this is a new subject of interest. Sir, my doubt is that Henry Poincaré has coined the name gravitational waves. Sir, how or from where this name gravitational waves have came from?
I don't know, honestly. So Einstein has used the word in German, Gravitationswellen, which gets translated to gravitational waves. So I guess the original word was used by Einstein, but in German, and the gravitational waves are a translation of this word in German called Gravitationswellen. I don't know more about that history.
Okay, thank you, sir. So I think we can wind up the section. On behalf of the Department of Physics, Bharat Mata College, and the Stride NG University, I would like to express our sincere gratitude to Dr. Ajith Parameswaran for spending his valuable time with us. And it is a wonderful beginning for our international conference. So thank you, sir. Thank you very much for a wonderful lecture on gravitational wave astronomy. And we hope we can expect the more collaboration in future also. Thank you, sir. Thank you very much.
Thank you, Manish sir, for chairing the session. With this, we have reached the end of the session. Once again, I thank Dr. Ajith Parameswaran sir for taking out time for us. Thank you, sir. Let me thank each and every one of you for attending this session. All are requested to attend the next session at 12 p.m. today. Thank you, everyone. Have a nice day.